Let's move to the fourth section in lecture 1. Actually, is we call a coupling of forces and flux. In previous sections, you already know how to get the entropy production rate to describe these three flow process, right? As long as you know identify the absolute temperature and measure the flux passing through your materials and know and figure out and know how much uh, what is the driving force applied on your material systems, so you can successfully get the entropy production rate per volume, right? But in this case, in previous section, you only deal with one driving force and one flux, right? But how about if there are two or more driving forces applied on your material systems? And definitely that will result to flux, right? And in this case is how to get or estimate the entropy production rate will be the issue in this important part in these sections. Okay, so before we tell you the results, how to deal with when we have two or more driving forces apply on our systems. So let's talk more about the entropy production. Based on the second law in thermodynamics, entropy actually, the change in entropy will be equals to absolute temperature, or that would be like the heat change divided by the temperature in the reversible process, and that would be the macroscope definition. And statistical thermodynamics tell you that the entropy also will be equals to the Kb is a Boltzmann constant, and times the log omega is the numbers of combinations. And we talk about combinations, so this description for entropy actually is a microscope definition. But no matter which kind of which point of view of the to describe the entropy, the change of the entropy in a system is equals to the change of entropy from the surroundings plus the change of entropy from the production by the systems. So what this means, you can think about that the total change of the system in the entropy definitely come from where? If you are the system, if you observe the changes in your entropy, so there's only two ways to contribute the entropy change in the system, right? Either the surroundings give you some entropy from the surrounding cells, or surroundings give you the entropy to you, or take out some entropy from you, or you guys, the system generate or produce the entropy constantly, right? So this is how to describe this as the change of the entropy in the system, either from the surroundings or the system generate the entropy by itself, right? So based on this, let's review the thermodynamic equilibrium state and the steady state flow process by this entropy point of view. Some people probably don't remember that when you describe the equilibrium state, you know the state function does not change with time. At this moment, you know entropy is also the state function. So in the equilibrium state, the entropy also does not change with time. So you will probably write down ds equals to 0. And in this case, actually, the system in equilibrium state, the system does not generate or produce any entropy. So ds entropy equals to 0. And this will be E0, this E0, and definitely surrounding is not going to give any entropy or take out any entropy from the system. So the S flux equals to 0. But how about the steady state flow process? One of the criteria for a steady state flow process is also the state function does not change with time. So in this case, state function does not change with time. That means the ds definitely equals to 0. There's no change in entropy of the system. But in steady state, this equals to 0. So, and you know what? The system, steady state, the system definitely produces an entropy, right? So this must be positive. So in order to allow ds0 equals to 0, so this flux turn, ds flux must be negative. So after sum of them, you sum them up, then you can get ds equals to 0, right? So this is a very big difference between the equilibrium state and steady state in entropy production part. And continue these results, then move to the steady state flow process. Based on this, we know the total change in the entropy change in the system equals to the ds produced from the entropy produced from the system plus the entropy change from the surroundings. So based on this, we want to this slide is going to show you how to deal with. We have the couple, we have 2 or more driving forces, and how these driving forces contribute to various different flux. So it will be a series of serious deviation here. So we start from the entropy production part or entropy part. So this equation we know that, so we take the deviated with the what? With the volume and also with the time. So you are going to get these results. Because if the ds is the entropy change for in production, right? So you divide it by the volume or also divided by time. So you got the entropy production rate per volume, right? So it's a sigma dot. And this one will be this one, this one will be this one, right? So you take so you got the partial S, partial T. And this S entropy change, actually the unit will be already divided by the volume. So it's a per volume, okay? And this one becomes this one. Some people probably will have some concern about this. So I write it down. When we derive the continuity equation for mass transport, we in previous slide we derived this result to you, right? The change of concentration, the change rate in concentration in the systems can express like equals to minus the gradient of flux, right? And this flux is atomic flux. So if I change this, instead of concentration, I use an entropy. That will be the entropy change rate, right? Per volume. Then this flux will become the what? The entropy flux. So will be this one. So this will be after you divide it by the volume and the time, so you will get this one. Okay, so this from here just move let's turn to the left-handed side. So you got the entropy production rate per volume equals to partial S partial T plus the entropy flux. You take the gradient on the entropy flux. So you have this one. So entropy production rate per volume equals to, can be also expressed like this, and this value much larger and or equals to 0. And next, based on this, we are going to have a series deviation to show you how to deal with if we have 2 or more driving forces here. So the detailed deviation, you can check the lecture note on page 6 and 7 to 7. But here I'm just directly move to the results here. If we have 2 or more driving forces, then how to get the entropy production rate per volume? So the results is come out like this. Absolute temperature times the entropy production rate per volume equals to what? This is a heat flux times the driving force to drive the heat flux, right? It's a minus temperature gradient divided by T plus the summation Ch1 times the driving force term, and it's a potential gradient minus potential gradient I. So it can be the electrical potential gradient, it can be the chemical potential gradient. So if I want to simplify or summary these terms, so we can write it down as a summation I flux I times force I. When you deal with the heat flux part, and this is the heat flux, and this will be the force minus temperature gradient divided by T. So now you know if we have 2 driving force, we just simply sum the flux times the driving force, then up, then we can get the entropy production rate per volume, right? So next, so let's move to an example. Before we move to this part, okay, we just use the first one. So if we have a metal bar now, there's the temperature gradient serving a driving force for heat flow, and the electrical potential gradient, which is serving the driving force for electrical current. And what is the entropy production per volume? Based on this result, we can simply formulate absolute temperature times the entropy production rate equals to what? Flux times driving force will be we have 2 driving force, right? The first one is electrical potential gradient, so you times the current density, plus the temperature minus temperature gradient divided by T, serving as a driving force for heat flow and the heat flux, right? This is the same, right? Okay, so you search, as long as I know this, then you can get divided by T, then you can get the entropy production rate for this metal bar, right? And this is electrical potential you apply on your system, so I believe you know the magnitude, you know the exactly magnitude. And this is also the driving force is a temperature gradient part. I believe because you apply the temperature difference, right? So I know this one. So now the question will be the current density and the heat flow. So let's do the other further description of further deviations related to the heat flux or the flux part. The flux J alpha actually equals to what? Equal to L summation beta, L alpha beta, F beta. So the flux, it turns out it will contribute directly from the corresponding driving force, but the other driving force, F beta, exists in this system, also contribute to this flux, and contribute by what? By we call the coefficient L alpha beta, by this. So if you take a look on your textbook, there's a sentence here. A beta field driving force F beta induces a partial flux of alpha quantity through a coupling coefficient L alpha beta. This description tells you that the other driving force will indirectly contribute some flux also will contribute some flux, right? So in order to make it more, hope we can, give you some more specific examples to help help you guys understand. So in this case, we notice this, right? So what about the current density and the heat flux in 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 this case? So based on these results, we can write down the heat flux. The heat flux JQ actually directly driven by temperature gradient turns directly, right? But because there's a exist of electrical potential gradient, and this electrical potential gradient, this driving force also contribute the heat flux by this L capital Q small q, right? So we can write it down like this. And I just want to explain the coefficient, how we write down the coefficient. The left-handed side usually will be serving the driving force. So L capital Q small q means the driving force is a small q contribute on heat flux. And this L capital Q here is the driving force, heat flux contribute the heat flow or heat flux. Driving force of FQ, heat flux, F capital Q contribute to the heat flux. So the same idea can be performed here. L small q capital Q means the driving force is F capital Q. Contribute on small q is the electrical current. And small q actually is the driving force as F small q is the electrical potential gradient contribute on electrical current small q. So based on this, we know the heat flux actually both these driving force will contribute to this heat flux. The same idea will be happen on the current part. Current actually directly driven by the electrical potential gradient, but because there exists a temperature gradient, it also contributes some amount to the current you measured in your system. And by what? So contribute some. So this L small q capital Q is we call the coupling coefficient. Some people probably will ask how much this temperature gradient or F capital Q contribute on the electrical current. So that will be by the L small q capital Q. Okay, so now we know this one. So we just substitute this term here and this term here. So we can get successfully get the entropy production rate per volume. Next question, probably you will come up from in your mind will be, Professor, we don't know L capital Q, L small q, capital Q, small q. We don't know these coefficients. So how to get the L capital Q and L or J heat flux and current? You can measure that, right? You can. There are two ways to either you know this coefficient, right? And either you can measure that in your system. And we are going to talk more about these coefficients. But here I can give you some idea about this coefficient is directly correlated with material property, specific material properties. Okay, and we will talk that more in following slide. Okay, so next. Back to here, even though I tell you you can get the detail deviation from this lecture note, but sometimes probably you will also want to know whether this equation is correct by other way. So here we suggest we use unit check to try to convince you that this equation definitely is correct. So first of all, we check the left term T times the entropy production rate. So what's the unit for T times the entropy production rate? Entropy production rate unit here would be the joule divided by what? By the time and by the volume, right? And entropy and also divided by the temperature, right? Because entropy is a joule divided by temperature, right? And temperature then delete of them, so you got the joule divided by the volume and the time period. So this term actually is the heat flux. So it's a joule divided by time and area divided by K. And the temperature gradient part will be the K divided by the distance. So we delete this term out. So you got the joule divided by time and also volume. So the same with this one. And this term actually is okay, also the flux, right? So the numbers of physical entities divided by area and time, and this is minus the potential gradient. Potential is a work, right? And you divide it by the distance. So if you check the unit, the upper portion will be in joule, because work, the unit for the work is joule, and the bottom part is the time and volume. So it's the same with this one. And the last part actually is dimensional flux times the force. Flux is the numbers of physical entities divided by time and area. Force is user force times the x, the distance divided by distance, right? So the upper portion is force times the distance is energy term is in joule. And number we don't have a unit for number, right? And this part is the time and volume. So it's the same with the unit here shown in here. Okay, so next will be some examples. I just want to summary. There are 3 flow process and the flux and driving force, and also correlated with some laws we learn related to this flux. So about the heat flow, the flux will be the heat flux times the driving force. Now, as we mentioned before, is a minus temperature gradient divided by T. Regarding to the heat flux, actually you learn the Fourier's law, right? The heat flux equals to minus thermal conductivity kappa times the temperature gradient. And the second one is the mass transport. The flux here is the atomic flux times the minus electrical is a chemical potential gradient, minus chemical potential gradient. And regarding to the atomic flux, you learn the Fick's first law. Atomic flux actually equals to minus mobility, concentration of the diffusing atom, and the chemical potential gradient. So the mobility actually is the velocity induced by the unit driving force. You use the mobility to describe how fast this atom moves along this material or inside this material, right? And the third part is regarding to the electrical flow process. Some people call it as a charge. The case is called a charge case. The flux here, depending on which unit you are going to choose. If you want to choose the numbers of charge atom or charge atom passing through your specific area, so probably you will use the JQ, the current density divided by charge of the atoms. Then you got the flux of the electrical charge, right? So the unit will be the number of the charge atom passing through, right? And you will times the driving force. As you know, the driving force can be the charge times the minus electrical potential gradient. So you put here, and you can delete the charge together. So for the electrical current flow, electrical part flow process, you directly use the flux part. You can directly use the current density times the minus electrical potential gradient, right? And previous, actually, you also learned Ohm's law. Talking about the current density also can equals to minus electrical conductivity times the minus electrical potential gradient. And as you know, minus electrical potential gradient can also equals to the electrical field. So low E is some people also, if you want to get the current density, some people use the low E, right? Okay. So today let's end it here.